So just reiterating, when we're talking about nomenclature of alkenes, some of the rules we have to follow. The pi carbons are always carbons 1 and carbon 2. We're always going to number so that if there is a substituent bonded at a pi carbon, that carbon will be carbon 1 of the pi bond, because that will give what we call the lowest possible numbering. We can have rings with 2 pi bonds. We would simply call these hexadienes. For example, if we can have a 1,3 cyclohexadiene, which would be a 6 carbon ring with 2 pi bonds that are what we call adjacent. The other ring that we can have would be a 1,4 ring. In that case, there would be 2 single bonds separating each pi bond. So 1 single bond separating 2 pi bonds, or 2 single bonds separating 2 pi bonds. Those are the 2 ring options for dienes. More rules for the numbering of alkenes, or more practice. This looks familiar. Okay. Hit that one. Nope. All right. So this is a case where the numbering is the same from either direction. From either direction, the pi bond would be at carbon 4. And we have a total of 3 branches: bromine, ethyl, and methyl. We're going to number so that the total number of branches has the lowest possible number, given that the pi bond has the same number from either direction. So I would start, it seems logical to me that to give the lowest possible number to all branches, we would start at the half of the molecule that has 2 branches instead of the half of the molecule that has 1. So if you start as I have numbered at the left side of the molecule where there are 2 branches, we get 1, 2, 3, 4, 5, 6, 7, 8 carbon molecule, pi bond at carbon 4. And write it down. Don't just put it in your head, because sometimes you will forget something if you only have it in your head. So we have the alkene at carbon 4. We have bromo at carbon 2. We have ethyl at carbon 4. And methyl at carbon 7. So when you name this molecule will be listing the substituents in alphabetical order: 2 bromo, 4 ethyl, 7 methyl, 4 octene. Okay, if we have, for the ring, we have that the pi carbons have to be carbons 1 and carbons 2. The lowest possible numbering would have me moving towards the half of the ring with 2 substituents. So if I cut the ring in half, 1 half across the pi bond, 1 half has 2 substituents, the other one has 1 substituent. I'm going to number towards the 2 substituents because that will give me the lowest overall numbering. So here I'm going to say carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. That would give us 3 chloro, 4 methyl, and 6 bromo. So that our name, if we write the substituents in alphabetical order, would be 6 bromo, 3 chloro, 4 methyl, cyclohexene. Vinylic carbon is the sp2 carbon of an alkene. It is the carbon that is part of the pi bond. That is a very important definition to remember. It's a definition that I stressed in chapter 4, but that you cannot forget throughout the Organic 1 and Organic 2 semesters. A second definition that you must know is the allylic carbon. The allylic carbon is the carbon adjacent to a vinylic carbon. It is usually, but not always, an sp3 carbon. It is simply the carbon bonded to the sp2 vinylic carbon. It is not the vinyl, it is not in a pi bond itself, although it could be if you had a diene. So allylic simply means next to the vinylic carbon, next to a vinylic carbon. When I'm talking about a diene, if I were to draw the following diene, I have 4 vinylic carbons and I will highlight in yellow, or let's list in yellow, for carbon 2, C3 is allylic to C2. C2 is allylic to C3. And C5 is allylic to C4. And C1, C2, C3, and C4 are vinylic. So that would be an example. So a carbon can be both allylic and vinylic, but it cannot be, an allylic carbon is usually not a vinylic carbon. Most allylic carbons are single bonds because dienes are not that common. So the vinylic carbon is the double bond carbon, and the allylic carbon is the carbon bonded to the pi carbon. Vinyl and allyl groups. A vinyl group is the smallest group that contains a vinylic carbon. An allylic group is the smallest group that contains an allylic carbon. This terminology is used for common names, allylic groups and vinyl groups, and we are not going to be using common names. So I don't want you to worry about naming things as vinyl or allyl halides. Basically, we're gonna skip this slide. Okay. Why we need to know what vinyl and allyl is because we're going to use these terms when we talk about reactivity. We're going to talk about reactions that only occur at an allylic carbon. And so allylic describes a specific structural feature that the molecule has to have in order for the reaction to occur. And so you need to know what allylic looks like. Okay? So for cyclohexenes, we are not going to name them as vinyl or allyl or methylene or chloromethyl groups. We'll have other names for them. For example, vinyl cyclohexane by the IUPAC name would be cyclohexyl 1-ethene because alkenes have a higher priority than alkanes. And